So time's up, so I guess we better get started. Well, let me introduce myself. My name is Daniel Donghyun Om at SQRT, and today all of you are in for a little treat. I'm going to be going over this new hot paper from Google, a seminal paper called Quantum Error Correction Below the Surface Code Threshold. And basically what their breakthrough was that on a superconducting device, they managed to reach something called the error threshold on the surface code, which hasn't been done before. And this can be considered a milestone in achieving the road to fault tolerance. So today I'm going to talk about basically what the main results of the paper are. And before I do that, I'm going to go over surface code for some of you who don't know what it is. And we're going to wrap up by, being a spoil sport and going over the limitations of this paper. So hope you have fun. So I'm going to quickly go over some background about the surface code. For those the uninitiated, the surface code is basically an error correcting code that's optimized for superconducting qubits. So the black spots you see and the white spots are actually qubits. What's the difference? The black spots, what we call measure qubits. Why are they called measure qubits? It's because we use them, we measure them. Shocker. And the one in white, they're the data qubits, is where we store our actual data. So as you can see, they're yellow and they're green measure qubits. The ones in green are called the Z measure qubits, and the one in yellow, they're called the X measure qubits. Now, the difference is that they're measuring different bases. So the Z measure qubit is measured in the Z basis, 0 and 1. And the X measure qubit measures in the X basis, plus and minus. So basically the Hadamard eigenstates. So why do we have these two measure qubits? Basically, their job is to force these qubits into stabilizer states, Z and X stabilizer states. Now, what's a stabilizer? A stabilizer is basically an operation that you put on a quantum state and you still get the same state. That's a stabilizer. So what we're doing here is we're forcing these states into Z stabilized and X stabilized states. And these are basically watchmen. They watch the data qubit, and if an error occurs, we perform stabilizer measurements on these qubits, and we use this data to help see what went wrong with the data qubit. So if we take a closer look, this is what actually the qubits are doing. These are basically shorthands for this little circuit right here. This I gate is basically a delay operation. And you see this G right here, that means the ground state. And we have these C naught gates here. So if A, B, C, D, these are data qubits, and we're basically controlling the data qubits, these are the control qubits, onto the measure qubit. So through this, we get something called a parity measurement, basically. So if the number of C naughts that are applied, if they're even, we just get, for example, if it's in ground state, we just get 0. If it's odd, it's a 1. So basically, essentially, what we've got is a parity measurement. And the circuit below is basically the same circuit, except we have Hadamars on both sides. So this is in the X basis, this is in the Z basis. So what we're doing here is we're applying C naughts onto the measure qubit. And at the end, you see this little thing. This is a projective measurement. So basically measuring the result. And they're going to repeat that. And we're going to keep repeating that. We keep pinging it in cycles. And the important thing is when an error occurs. So what we're doing as an error occurs is we take these projective measurement results, and through these results, we throw them into what's called Edmonds min-weight algorithm. Well, I'm not going to go into detail what this is, but basically, you can just think of this algorithm as detecting what's wrong. So if something goes wrong, as an error occurs, if an error occurs, then these projective measurement results don't match with the non-error case. And we can detect this through what's called Edwin's Minway algorithm. Now, this is the classical example. As you later see, some people like to replace this algorithm with a neural network. This is what actually Google did. And it doesn't matter, to be honest, but it's more of a personal preference. They both have advantages and disadvantages. But the main point is that these projected measurement results are used to correct the data qubit. So is this like fail-proof? No. It actually has the limitation is that you can't detect dense and long errors. So as you can see, the placement of the measurement qubits, if we go back here, they're all kind of locally around the data qubit. So this little thing can only detect errors on these 4 little data qubits. It can't detect an error on this corner right here. Okay, so as you can see, the boundaries have less measured qubits around them. So this is a limitation, of course. Okay. So once we we can detect local qubit errors and can use this information to correct them. Now, what's important here is that we have physical errors. Yes, I have a question. Yeah, you can't detect leakage errors. You can detect Pauli errors. Yeah, mostly Pauli errors. They're mostly errors that are local. Like, for example, if you have like crosstalk here, you can't detect it with that. So mostly the surface code is kind of it's a good tool for quickly detecting local errors in real time and quickly correcting them. Yeah, you can detect dephasing errors as well because you can just decompose them into Paulis. So the important thing here is that we have 2 error rates in this situation. We have the physical error rate, which is the error on the data qubit, and we have something called the logical error rate, which is the error on what's called the logical qubit. What's a logical qubit? Basically, this entire pattern, this single entire pattern is, you can say, is a logical qubit, basically. For the uninitiated, logical qubits are basically the basic building blocks that are error that you can correct the error for. For example, this entire thing, if we can think of it as a qubit, we are using these measure qubits to detect errors within this qubit. So basically, logical errors, this entire thing is a logical qubit. And the errors, if the error correction fails, we get what's called a logical error. So error correction isn't 100% foolproof. So we can have some errors. The error correction process fails sometimes. And when this fails, we get what's called a logical error. So the logical error rate is the error of this entire error correcting process. And this is the actual important thing because it doesn't really matter if you have a high physical error. If the logical error is low, for all intents and purposes, it doesn't matter at all. So basically, our goal here is to reduce this logical error rate. Now, so how is the physical error and the logical error related? This entire expression is the only thing, if you had to forget everything else, this is the one thing you shouldn't forget, okay? This is basically the relation between the rate of error of the algorithm, the logical error rate, and the physical error rate for the surface code. Now, this term here is what's in the money, basically. This thing is what we wish to keep under 1, okay? If we cannot keep this under 1, error correction is basically unfeasible. So we call this special value 1 over lambda. So this is called the threshold probability, a little bit of a spoiler, over the physical error. So when this thing is above 1, when this fraction is below 1, those of you who's taken high school algebra, you can see that as d increases, this logical error decreases. Now, what is d? D here is basically something that's called the surface code distance. I'm not going to go into too much detail about what code distances are, but for all intents and purposes, you could just think of it as a number of physical qubits. So if I have a surface code distance of d, I have a physical qubit number of 2d squared minus 1. So this is basically the size of our logical qubit. So if I increase the size, when this is less than 1, you can see here, the logical error actually decrease. I can make it arbitrarily low as long as I have a big enough logical qubit. But if this is 1, well, disaster strikes because we're using more money to increase the error, which, yeah, we don't want unless you're, I don't know, unless you're a mad scientist. This is not what we want. So the important number here are these 2 errors. And the most important number in here is the error threshold. So our long-term goal here is to keep this physical error rate below the error threshold. And this is what Google finally managed to reach. So before Google's paper, this was, this was considered possible, but no one's actually done experimentally before Google came along and actually did it. So our goal here is to maximize this lambda and keep under the error threshold. So how do we find the error threshold? Well, actually, it depends on the situation, depends on it depends on actually a physical situation, the architecture, depends on the code distance size, it depends on a lot of other factors. So practically, we can't actually determine the threshold through a analytic form, but in practice, how do we can tell whether we've reached a threshold by basically plotting the logical error and seeing if it decays with the code distance. So what you're seeing here is an example of this decay graph. Basically, NQ is the number of qubits required in a logical qubit. And basically, you can say this is like a flipped logical error graph. So if you look at it this way, it's actually decreasing as single step error rate decreases as well. So basically, if you get this sort of graph, you can tell that P is less than the error threshold for all intents and purposes. Now, if you want an exact expression, the most common method to use is actually by a simulation, a Hamiltonian simulation, and then you see whether you get this exponential graph. But in practice, there's no way to actually get it through an analytic expression. So this was the very long intro. Now I'm going to go over the main results of Google. So here's a little summary for those who are in a hurry and need to go home right now. Google basically managed to get this lambda over 2 for up to a code distance of 5. So that's basically a logical qubit of 49 physical qubits, and distance 7, about 105 qubit surface codes. So they did it for about 72 and 105 qubits. High distance repetition codes, basically 72 qubits, we're considering this high distance for some reason, implemented with correlated errors about 10 to minus 10. So this is the physical error rate. And the third is this is a bit important, decoding real-time possible. So before early 2020, what you would do is basically decode the data after you've done all the measurements and look at the data. So basically the min weight algorithm I showed you, that's a post-selective algorithm. What Google did, they used a real-time decoder. So as errors occur, you're decoding them in real time, basically. Within the 1.1 microsecond cycle duration below the threshold, this is important because a cycle, you want this decoding to be as quick as possible to avoid possible errors coming in. And Google actually managed to do this. So it's a great technical achievement. So this is the surface code Google used. It's similar to the one you've seen, except you have these additional qubits in green. Now, these qubits have a special job. Their job is to remove leakage errors. What are leakage errors? Basically, qubits, they're called qubits because there's 2 states, 0 and 1. But if you somehow manage to make it to state 2 and 3, we're not going to use these. They aren't in what's called the computational Hilbert space. So any error that causes 1 or 0 to turn to 2 or 3 or more are called leakage errors. And these are really hard to correct because we don't know the original destination. Not the original destination, the original origin. Was it a 0? Was it a 1? You don't know. So leakage errors are quite troublesome. These qubits jobs are there to correct these leakage errors. And basically, the algorithms are quite similar to your conventional surface code. You prepare using the measured qubits, the state into a product state of these X and Z stabilizers, and you measure the parity, and you send it to the decoder, but this time the decoder is a neural network. So basically, you have a neural network that's pre-trained on data, and you're going to use this neural network to decode it in real time. And afterwards, you run the leakage removal task. For example, if it's 2, or for example, if some qubits go to 2 or 3, you're going to use these qubits to reset this. So these are basically like dual rail qubits. I won't go into too much detail, but basically these qubits' jobs are to detect where the leakage error occurred and what the original qubit state was. And finally, you measure these static qubits and you correct them in real time using the decoder. So here, the proportion of parity measurements that detect an error, that would be called a physical error. And the total failure rate of this algorithm would be the logical error. So this is the graph, like Google's, taunting around and saying that we did it. So as you can see in 2023, that's just this last year, you see this extremely steep increase in the logical error probability for an quantum error correction cycle T. So a quantum error correction cycle T is just how many times you did the quantum error correction algorithm. And you can see as the distance increases, this logical error probability is decreasing. So what does this mean? This means we've actually reached our threshold. If you're above the threshold, you would see the opposite. You actually see it goes the opposite direction. You will see it actually increasing. So you're just wasting money. But this is the first time this actually happened. So we're decreasing logical error probability. So what Google basically managed to do, it managed to improve the physical error rate using different fabrication techniques such that it reached a threshold. And they also used a real-time decoder to reduce the number of time that errors are allowed to occur. As you can see right here, lambda is 2.14 above 1, which means it's below the error threshold. And you can see this exponential decay graph. This matches with the simulation Google did to find the threshold probability. Okay. As you can see, the physical error still increases slightly, but it's still below the threshold. Yes. Threshold error rates. Google didn't actually, it's not actually in the main paper because there's not really much point because it depends on the situation all the time. So, but yeah, that's all I can say. It's not actually in the main paper, so I don't have access to that information. Yes. What error rate are you talking about? The logical error rate? Oh yeah, this is the dashed line is the physical qubit. Yeah. 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 You're saying the logical error is higher than the physical error. Yeah, that's actually true. But what Google's saying that it decreases. So 3, it sucks. Yeah, it sucks. 3 sucks. But hey, 5.7 is great, And then if we could get enough money, grant money from this paper to get it to 9, hey, it decreases. So yeah, I can see what you're saying. It sucks. Yeah, it does suck. But 5 and 7 doesn't suck. So this is why they get published. Maybe in Nature. I think they did submit it to Nature. Yeah. Yeah, you could do that, yeah, but there's just like this error here, so yeah, maybe you could probably estimate it through this, but there's no they didn't actually put the exact value in the paper for some reason. So you have 7.7%, 8.5, 8.7. It does increase, but this it increases. But why does it increase? Because of course, if you have more qubits, we're coupling between the errors. So they after showing this graph and doing the little victory lap, they also measured how sensitive this is to extra errors. So they actually deliberately increased injected errors into the circuit. So basically, this is your basic surface code circuit, except the injected errors. See here, through this gate, the injected errors here. DD refers to dynamical decoupling. For those who don't know what it is, it's basically a signal pulse sequence. For in superconducting qubits, they use pulses as gates. And dynamical decoupling is a series of pulses that are used to mitigate errors. So this is just always there. This is your leakage removal procedure. So what they did here was artificially inject errors to test how sensitive it is. And this is the result. So basically, here you see they have P detect, which is the probability of detection of errors. And they argue that this is a good proxy for 1 over lambda. So for all intents and purposes, this is just 1 over lambda. And you can see we have a higher decay rate for a higher D right here, which is good. We want that. So that's what they're saying. Hey, we have a higher decay rate for a higher D. And the good thing here is that as they injected errors, this logical error per cycle is maintained for long periods of time. So it's stable, which is necessary because you don't want it to be here and then suddenly jump right here, which would be quite problematic. So basically, this graph is saying that, hey, our value is stable and our value decays faster for D. So it's like insensitive enough. If it was too sensitive, this wouldn't be maintained for long hours. So they also determined something that was called the error budget. Basically, like what type of errors make up the most of my physical error. As you can see, we have leakage here. It's an annoying little thing. Not much you can do about that. We have CZ, correlated errors from CZ gates. We have local gate errors, local measurement errors. And we have leakage errors and unwanted interactions. So 17% of the error budget is made up of correlated errors. Surface code is good at correcting non-correlated errors. So basically, what Google's saying is 83% of our error is correctable by a surface code, which is good. Good. Let's say this was like 70%. So it doesn't really matter how much of a logical error rate you get, how large of a logical qubit you get when you can correct the majority of these errors. So this is basically what Google's saying. Hey, this is practical. We can use this. Now, there's an objection. Hey, 3, 5, 7, that's great. What about 10 or 20, 30? So Google actually tested that. They found the money somehow. They tested that. So you have a code distance of 5, 10, 15, 20. So they did it to around like 20, 25. And you can see the results from 2023 is here, which sucks. It sucks really bad. But the new results from fabrication techniques that they used is right here. It's much better. So for the same exponential scaling, for high distance repetition codes, they actually found a lambda was 8.4. In this case, it was actually higher in this case, which is great. And this is just the same graph. So as you can see, D equals 29. They did it to around D equals 29. This exponential decay is quite nice. So basically, this is good news. Yes. Yeah, I believe this is actually a projection from their data. Yeah, a projection from data. So what they're saying here is that if we manage to get the 29 up to 29, it would 700, it will greatly increase. So I believe 7 is seven is the maximum, actual experiment. So this is actually projection right here. So we've looked at the main results. So basically, to recap, they did reach the error threshold for 357 actual experiment. They found a lambda was 2.14. They also found that only 70% of the error budget is used by problematic errors for the surface code, which is good. They also found that through a simulation, that for high distance repetition codes, you can actually reach a lambda of 8.4. But this logical error rate is maintained for long periods of time. Now there's a catch to this. There's a catch, of course. Everything in life has a catch. So the big problem is that there's a noise floor, which means that there's, for the current technology, the current fabrication techniques they used, they can only reduce this physical error to 10 to the minus 10, which is problematic because you need way more than that for a fault-tolerant computer. Okay, so it's party pooper, and I know. Now, the main problem is that at certain regions of the circuits, so this is the monitoring of the circuits, and the detection probability, which is basically, you can say 1 over lambda. So if this thing is large, it's not good. Okay, it's a high rate of error. You can see these spikes here, which is annoying because these spikes mean that there's this noise floor of 10 to the minus 10. And these always occur. Now, the problem is that we don't know what these are. They postulated that it might be cosmic rays, but the rate of decay is too slow for that. So no one knows what this is. And if you want to get a job at Google, maybe you could provide an explanation of this. Like, this is the quickest way to get a job at Google. So basically, the greatest challenge here is that we have these error spikes that no one knows the origin of. So they tested it for several different devices. They found the same error spikes, same exact scale, particularly in this 4th quartile right here. So no one knows what it is, but it's there, and it causes a limitation on the amount of error we can decrease. And the second one is actually what was touted as its strength, is the reliance on neural networks. So basically, one selling point of quantum computers is that they're like power efficient. But the problem is, if you need a large neural network that's being trained on lots of data, that costs money, that costs a GPU, that costs a lot of power, which decreases the power efficiency of our algorithm. So Google used a real-time decoder to reduce the amount of errors that could leak in, but at the same time, they sacrificed power efficiency. So the best method so far, real-time decoding, that's this graph right here, neural networks had the best performance, but the problem is they're expensive. Yes. Fully decode the error correcting codes. I don't actually know. It's actually in this paper, but I didn't actually read it. I didn't actually read the paper, but I know that it won't, as the logical qubit increases, the amount of data you need is exponential. So that's a problem, yes. 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 Yeah, yeah, yeah. Yeah. Yes. Yes. I guess, yeah. I guess it is kind of different. Yeah. Yeah. So basically the point is they use neural networks, which costs money, which reduces the efficiency, I guess. So if there's another method that you can use without neural networks, it would be an improvement to the energy efficiency. Yeah, but so basically, to summarize these limitations, because of this and this, the error rate we need it's still out of reach. It does decrease, but it's a lot. It's still a lot. So to achieve an error rate of 10 to -6, you need 27 distance codes, which means 1,457 qubits per logical qubit. So it's still, still not technically feasible at the moment, but we've made the first step because for the first time ever, the logical error rate actually decreased with the code distance. Okay. So in conclusion, although it still sucks, it sucks less. And we're on the first steps to reaching a fault-tolerant quantum computer, which doesn't suck at all. Yeah. So that concludes my presentation, and I'll be happy to collect any questions you may have. Thank you.